Okay, so good afternoon, dear colleagues and ladies and gentlemen. I warmly welcome you to our webinar today. My name is Wenchao Xue, and I'm the director of the Asian Institute of Technology, Belt and Road Research Center. The AIT Belt and Road Research Center was established in 2019 with the vision to serve as an international hub for collaborative and innovative research for the sustainable development in the Belt and Road region. Since its establishment, we have been participating and collaborating in Belt and Road projects, promoting the collaboration with China's and other Belt and Road countries' universities and organizations, and supporting young scholars and students research and study in the Belt and Road region. In our earlier webinar, in mid-August 2021, we had an initial discussion on the Digital Belt and Road Program and its great potential to empower the global sustainable development. To further facilitate knowledge sharing and exchange the experience on the Digital Belt and Road and its roles in supporting sustainable development, we have been working closely with our partner organizations, including the National Research Council of Thailand, Digital Belt and Road Program, and the Mahidol University in the past months. And today, we are very pleased to jointly deliver this DIBA Expert Talk Series on Big Earth Data for the Sustainable Development Goals. The Digital Belt and Road Program, or so-called DIBA, initiated in 2016 by the Chinese Academy of Sciences, and is aiming to improve the environmental monitoring, promote data sharing, and support policymaking using big data on Earth observation. With a strong regional collaboration, DIBA has committed to put its research efforts on investigating the index and indicators to fit into the United Nations Agenda 2030 and the Sustainable Development Goals, and deliver an open access data platform for the researchers, policymakers, and the public for tracking and studying the development and changes in the Belt and Road region. This webinar series will be composed of 4 special lectures focusing on different SDGs, which are SDG 2 for zero hunger, SDG 6 for clean water and sanitation, SDG 11 for sustainable cities and communities, and SDG 14 for life underwater. I would sincerely express my appreciation to our guest speakers, Dr. Lijun, Dr. Junsheng, Dr. Wu Haifeng, and Dr. Xing Qiang from the DIBA program for kindly sharing their experience, expertise, and research on developing the Earth observation and big data technologies to address various SDG issues. I would also like to extend my thanks to my colleagues from Asian Institute of Technology for kindly moderating each special lecture in today's event and also the ones on this Thursday, 14th October. So I sincerely welcome your participation and wish all to have a fruitful communication and discussion in our webinar. Now I would like to call on my colleague, Dr. Salvatore Verdis, to moderate our first special lecture by Dr. Lijun. Thank you very much. Dr. Verdis, please.
Good afternoon. Thank you, Dr. Wenchao, and good afternoon, everyone, and welcome to this first presentation of the series focusing on SDG. And it is my pleasure to moderate this session that will see a presentation first given by Professor Junsheng Li, and then a Q&A session will follow up. So please stay tuned until the end so that we can focus also on discussion. So it is my great pleasure to introduce Professor Junsheng Li. He will be presenting a presentation focusing on surface water quality monitoring and assessment using remote sensing. Professor Li works at the Aerospace Information Research Institute of the Chinese Academy of Science, and his research focuses on remote sensing of water environment. He published more than 100 papers in relevant scientific journals, international scientific journals. He received the second prize of China National Technology Invention Award, and his research has been widely awarded by the Chinese Academy of Science, and also reported by several news media, including China Central Television. He also is a member of Ocean Color Coordinating Group, IOCG. He also board member of the Journal of Remote Sensing. Today, Professor Li will be presenting a very interesting presentation where he will be showing results on remote sensing-based colorimetry applied to the estimation of trophic stake index and in inland water transparency. I had the chance to read this interesting presentation in advance. Professor Junsheng Li, thank you very much to be with us.
Yeah, thank you. Thank you, Dr. Wallace, and thank you, Dr. Xue. I'm very glad to have the opportunity to share our experience of the research of our on surface water quality monitoring and assessment using remote sensing. Let me share my screen.
Yes, it is.
Okay, thank you. Thank you, everyone. Good afternoon, everyone. My name is Junsheng Li. I'm from International Research Center of Big Data for Sustainable Development Goals, and also from Aerospace Information Research Institute, Chinese Academy of Sciences. My topic today is surface water quality monitoring and assessment using remote sensing. First, the outline. My topic includes the 4 parts. First is the basic principles in surface water quality monitoring using remote sensing. I think maybe most of the audience are not doing something like the water quality monitoring. So I would like to outline some basic principles of the water quality monitoring by remote sensing. And then I will introduce some recent publishment of our group. And the first is the water color index. We also call it the FUI, monitoring using remote sensing. And then I will introduce the trophic state assessment using remote sensing. And the last is the water clarity estimation using remote sensing. And let's move to the first, the basic principles in surface remote sensing. As we all know, remote sensing technology mainly include the optical remote sensing, the thermal infrared remote sensing, and the microwave remote sensing according to the electromagnetic spectrum used. For the optical remote sensing, it mainly includes the visible and near infrared light, and the thermal infrared is use the thermal infrared, and micro use the microwave. And different remote sensing technology have different applications in surface water quality monitoring. For optical remote sensing, it can penetrate the water surface, and it can get the information below the water surface. So it can do many things in water quality monitoring, like it can estimate chlorophyll A, the concentration of the algae, and it can estimate the total suspended matter, and also the color dissolved organic matter, and the water clarity, the algal bloom, and also aquatic plants, and also the oil spill. Well, for the thermal infrared remote sensing, it can only detect the water surface temperature, and then the water surface temperature can be used to estimate the thermal pollution. For the microwave remote sensing, it can only detect the surface state of water, so it often is used to detect the oil spill. And algal bloom are also, especially for the blue algal bloom, the algae flow to the surface. It can affect the surface state. So microwave remote sensing can also be used to monitor the algal bloom. So for the comparison, we can see that the optical remote sensing have the most applications in water color, in water quality monitoring. So optical remote sensing is the most widely used in water quality monitoring. And optical remote sensing can reflect the water color, because the optical remote sensing mainly use the visible and the near infrared and mainly visible light. So it can reflect the color information of water. So use optical remote sensing to monitor water quality is also called water color remote sensing. Under a clear sky, different water bodies often show different colors. There are 4 kinds of water body in China, and it's very typical. There is a Namco Lake in the Tibet plateau. We can see the water is very blue. For the Yellow River, it's very yellow, the water color. For the type lake with cyanobacteria bloom, we can see a green color of the water. For black and older water in some in the city, it's highly polluted water. We can see the color is almost black. And I think in Thailand, we can also see some water bodies with different water colors. Maybe not extremely like these 4 kinds of water bodies, but we can also find, I think, the blue, the yellow, the green, and maybe the black water color. Well, before we, I have just mentioned water optical remote sensing use the water color information to estimate the water quality. So first of all, we can ask a question: why different water colors show different colors? Why different water bodies show different colors? If we can we can understand the mechanism of behind the water color, then it makes a good basis for optical remote sensing of water. First, we can see the reflectance of different water bodies. For the blue one, it is the reflectance of the Namco Lake. We can see it reflects, the reflectance is very high in the blue region, the blue wavelength region, and it reflects more light in the blue wavelength. So it will, we can see the blue color. For the yellow river, the blue one, the reflectance have high value on the blue wavelength region. And for the type lake, the green one, we can see a very high peak reflectance in the green wavelength region. And the black is black and older water reflectance. We can see the reflectance are very low in almost all wavelengths. Well, the water body, in the water body, there are some absorbed and some suspended materials. And these materials can absorb or scatter the incident light. And it can determine the reflectance of water and then determine the color of water. Here is the incident light. It can be absorbed by water and it also can scatter by the water. And the absorbed water is the energy transferred to heat or something else, while the scatter, the energy redistributed into other directions. The scatter in water mainly include two kinds of scattering. First is the molecular scattering. It is scattered by the water molecule. It is also called the Rayleigh scattering. And the other kind of scattering is the particle scattering. It is scattered by the particles in the water body, and we can use Li scattering to model the scattering by particle. For the Rayleigh scattering, it occurs when the particle radius is far less than the incident light wavelength. For the water molecule, it is Rayleigh scattering. And here is the calculation formula. From the formula, we can see the reflection, the scattered light density is inversely proportional to the force power of the wavelength. So it reduces rapidly with the wavelength increase. Well, for the particle scattering, which can be modeled by the Li scattering, it occurs when the particle radius is far or equal to the incident light wavelength. Here's the calculation formula. We can see the scattered light is not proportional to the wavelength. We have in the water, there are mainly four components. Since the water has the pure water, the H2O, and it also has the absorbed material. We can call it color dissolved organic matter. It is mainly tannins or released by decaying substances. It also includes the phytoplankton. It is a tiny algae suspended in water, and it also has non-phytoplankton suspended matter. It is suspended substances other than the algae. And the pure water absorbs the radiation transmitted in the water. We can use the AW to represent the absorption of the pure water. The AW increases rapidly as the wavelength increases, while the pure water also scatters the radiation transmitted in the water. It's mainly Rayleigh scattering. We can use it as a BW. BW decreases rapidly as the wavelength increases. The absorption and the scattering of pure water are almost invariant in all kinds of water. So we can just use the AW and the BW measurement from literature. We don't need to measure it by ourselves. For the CDOM, the CDOM has an obvious absorption effect, but the scattering effect can be ignored. The absorption of coefficient of CDOM decreases rapidly with the increasing wavelength, and we can measure the absorption spectrum ACDOM in the laboratory by a spectral photometer. We can use a vacuum pump to filter the water, and we can compare with the pure water to monitor the ACDOM. And for the non-phytoplankton suspended matter, the absorption of the spectra of non-phytoplankton suspended matter decreases also rapidly with the increase of wavelength. And for each water body, we can also measure the absorption AD, and we use also the future equipment, and we can measure the transmittance of the filter membrane compared to the black membrane using a spectrophotometer. And for the absorption of phytoplankton, it contains a variety of pigments, and the most important of which is the chlorophyll A. And the absorption of all pigments in the phytoplankton constitutes the absorption of spectrum of the phytoplankton. We can also measure the APH, the absorption in the laboratory. And for the the total suspended matter, it actually includes the phytoplankton and also the non-phytoplankton suspended matter. Both of them are particles, and the scatter particle scattering. And we can use mixed scattering to model both the phytoplankton scattering and the non-phytoplankton suspended matter. So we use the scattering of total suspended matter to represent the two parts. And here is a measurement of the scattering of total suspended matter in a lake in Taihu. And we can see the scattering very slowly with the wavelength. And for a water body, there are 4 materials in the water body. And the absorption and scattering effect are additive. So we can get the total absorption by adding the 4 components of the absorption. And for the scattering, we can add the scattering of water and particles. And so we can answer our first question: why different water bodies have different colors? The answer is different water bodies have different proportions of water components. The water components include the pure water, the phytoplankton, the sedum, and the non-phytoplankton suspended matter. Different water bodies have different proportions. Some water has the most proportions of pure water, some have the most of phytoplankton, some have most of sedum, and maybe some have the most proportions of non-phytoplankton suspended matter. And the different water components determine the absorption and scattering of light, and then lead to the different color. We can see directly from some examples. For the highly turbid Yellow River, here are the absorption and scattering of each components. And for the scattering, we have the particle scattering and the molecule scattering. And the particle scattering are most higher than the radius scattering, the water molecule scattering. But the scattering of the particles very slowly with the wavelength. So we cannot tell the water color from the scattering of the particles. And we have to, and the water color mainly depend on the absorption of the water body. If in some wavelengths it's absorbed more light, and it will reflect less light outside the water surface. And for the black one is the total absorption of water. And among them, we can see the red one. The red one is the absorption of the non-phytoplankton suspended matter. It it dominates the total absorption of water. And also the blue one is absorption of pure water. And the non-phytoplankton suspended matter and both the pure water, it dominates the water absorption. And we can see there is a minimum of absorption around the blue wavelength. And so it absorbs less light in the yellow wavelength, and it will reflect more yellow wavelength. So we can get more yellow wavelength reflected, and we can get the yellow color of the yellow river. For the type lake with a cyanobacteria bloom, and we can also see there are many particles. The phytoplankton are also particles, and the particle reflection are much higher than the water molecule scattering. But also the particle scattering very slowly with wavelength. So the scattering does not lead to the watercolor, and the watercolor is determined by the absorption of the water body. And we can see the total absorption of water body, the black one, it reflects light. It absorbs less light in the blue wavelength, and then it will reflect more green light. So we can see the green color. And in the total absorption of the green light, the absorption of phytoplankton determines the shape of the total water absorption. This is why the type lake is green color. And for the Nabucco lake, there are very few particles. It's very clear. There are few particles in the lake. And we can see this is a scattering of the water molecule is higher than the particles. And if we just see the scattering, we can see it reflects more blue light, and we can see the blue color. And also we can see the absorption. The absorption, we can see the black one, it also absorbs less light in the blue region. And and it is dominated by the pure water. The total absorption is dominated by the pure water absorption. So from both the scattering and the absorption, it absorbs less water, less light in the blue region, and it reflects the more light in the blue region. So we have the blue color of Nabucco Lake. And for the black and older water, we can see the particle scattering is higher than the water molecule, but it's rather low because there are less particles in the water. The scattering is lower than the absorption. The absorption absorbs all the light in all wavelengths. So we can see all the wavelengths have less light reflected by the water. So it has a dark reflectance. So we can tell the mechanism behind the watercolor and the different water components proportions can determine the absorption of water, and then it determines the reflectance shape of the water, and then it determines the watercolor. And we can deduce the theoretic basis of watercolor remote sensing under the premise of that the spectral characteristics of the incident light source it is mainly the solar spectrum are known. We can measure the solar spectrum above the atmosphere, and we can use the atmospheric correction to get the solar spectrum under the atmosphere. Here is the we can get from before the incident light penetrate into the water. And then we can use the remote sensor to receive the spectrum reflected by the water body. And after our study, we can know the substance content in the water. We can know the absorption and the scattering effect of various substances. So then we can retrieve or inverted the substances content in the water. This is the basis. We know the incident, we know the reflected, and we know the mechanism in the water, within the water. Then we can use the reflected light to invert the water substance content in the water. Here is the theoretical basis. Although we know the theoretical basis, there are many difficulties of surface water quality monitoring using remote sensing, because the inland water bodies have complex water features. As we have mentioned, there are 4 water components, and it can vary seasonally and regionally. And in different regions, it have clearly different colors, and it has very different optical features. So there is for this background, there is lack of universal water quality monitoring models using remote sensing, and there are few remote sensing products for large-scale inland waters. Here is the NASA Global Water Chloride Fuel A products, and it has it products of mainly the ocean water, and while in some clear water like the Great Lakes, it also has products. But for some turbid lakes, like in the Yangtze River plain, we can see there are no products. Well, since there are some difficulties, and how to overcome the difficulties of the surface water quality monitoring by remote sensing, we think chlorophyll and suspended solids and etc. are bare geochemical parameters, and they tend to have regional and temporal differences. And optical remote sensing provides optical data, and it is hard to retrieve bare geochemical parameters in all regions and all types. But we think it is easier to estimate optical parameters of water using optical remote sensing. It makes sense, right? So we think one of the optical parameters of water is water color, as I have just mentioned. But how to describe the water color quantitatively, not qualitatively, how to quantitatively? Well, we can find there is an index with a history of more than 100 years used to characterize the color of water. It's called the Fourier index. These two are the 2 authors who invented this kind of method. And it uses a FUI colorimetric table and to measure the water color. We use the table to compare with the water color, and then we can record the water color. And here is a record of global ocean observations of the FUI in recent 100 years. We can see it exaggerated. Actually, it's a very small sample size. And here is we can tell the water FUI by the visual comparison. But how to compute the FUI based on satellite remote sensing, like the MODIS data, which is very widely used the remote sensing data. And for MODIS data, it has the blue, green, red bands. So we use these three visible light bands. We can compensate the RGB color space. The RGB color space. We can translate the RGB color space to the CIE color space. Here is the steps, and we use the RGB to calculate the CIE tristimulus XYZ, the big X, big YZ. And then we use the BXYZ to calculate the chromaticity coordinates, the small x and y. The small x, y is the coordinate of the CID color space. And this is the x, and this is the y. And we can define the hue angle. The hue angle, this direction is 0, and we can tell the hue angle increase in this direction, and it is 360 degrees when it come back. And here is the formula. We use the x and the y to calculate the hue angle. Well, the MODIS data, the blue, the three visible light have different band sightings. We can use the simulated data to correct it, the influence of the band sightings. And here is the correction. And after that, we got a lookup table. When we get a hue angle, we can get the FUI. Here is the lookup table. And here is the flow chart of the data processing step. First we got the MODIS reflectance data. It's a surface reflectance, not water leaving reflectance. And first of all, we made a water leaving reflectance correction. And after that, we made a water segmentation. We derived the water mask. And we use the RGB, three visible bands to calculate the hue angle, and use the FUI lookup table to get the FUI. And here is the validation of our FUI results, and it has a very pretty high accuracy. And use this technology, we applied the methods to calculate the FUI, the watercolor index of global large lakes from 2000 to 2018. And here is the average of the global large lake watercolor index. And we can find some spatial distribution rules. We find that the water bodies with low FUI are mainly distributed in the cold regions, such as the high latitudes and the plateaus, including the Tibet Plateau in Asia and the North Europe. And the water bodies with high FUI are mainly distributed in the low latitude area or the plain areas, such as the plain of Eastern China and Central Africa, and etc. And we can also analyze the temporal changes of FUI of global large lakes from 2000 and 2018. And we found out that the FUI, of the 36% of lakes decreased significantly, mainly in Qinghai Tibet Plateau and the cold regions of Arctica and the Antarctica. And only 8% lakes have a significant increase in FUI, and the distribution is relatively scattered. And then we move to the next topic, the trophic state assessment. Well, the trophic state of a water body is a relative expression of the biological production of the lake. The trophic state level includes the allotropic, mesotrophic, and eutrophic. Eutrophication refers to abnormal reproduction of algae and other aquatic organisms due to the excessive nutrients in the water body. And the harm of water eutrophication is to destroy the aquatic environment, to harm aquatic animals, and to threaten safety of drinking water. Well, the traditional method of trophic state monitoring by remote sensing is first retrieving chlorophyll A concentration by remote sensing, like this, and then compute the trophic state index, TSI, by a formula of chlorophyll concentration. And we can get the advantages or potentials of remote sensing based methods. It has a wide coverage, low cost, and dynamic monitoring capacity. But it has the difficulties, just I have mentioned. The optical properties of inland water are complex, and there are big regional and seasonal differences in the optical properties of inland waters or water bodies. So there is no universal inverted model of chlorophyll inland waters. So under the background of immature chlorophyll retrieval of large-scale inland water in the world, how to quickly realize remote sensing estimation of trophic state of large-scale inland water. And our method is to skip chlorophyll A and directly evaluate the trophic state level according to the water color index. And just we have mentioned the Fourier U index. We can tell from the color. For the green type lake, we can tell it is eutrophic. And for the blue Namaco lake, we can tell it's the oligotrophic. And for the color in between in another reservoir, we can tell it's a mesotrophic. But how to classify the trophic state level based on what color? And we can use the simulated data and in situ measure data to analyze the relationship of the TSI and the FUI. And from this analysis, we can tell for the FUI lower or equal than 6, this part, they are oligotrophic. And for the FUI between 6 and 7, mainly this part, most of them are the mesotrophic. And for the FUI greater than 10, they are mostly eutrophic. But there are some misclassifications, like the blue in the blue rectangle. And we further analyze the data of the misclassification. And we can find out that for the red, this is the red reflectance. For the red reflectance lower than this threshold, most of the water belong to mesotrophic. And for the water greater than this threshold, they are mainly dominated by the high concentration of CDAW. They are not the mesotrophic. So we can use the red reflectance threshold and combine it with the FUI threshold, and we can get the decision tree of the trophic state. We use the FUI and the reflectance of red band. We can determine the trophic state of oligotrophic, mesotrophic, and eutrophic. And this is the validation. We got 101 lakes data from around the world. we get from literature, and here is the confusion matrix, and here the overall accuracy is 80%. And here is the result, the global large lakes, the average trophic state in 2012. We can tell the spatial distribution of the trophic state of large lakes, and we can find the numbers, and we can tell that the eutrophic lake are more than 60%. And so the eutrophication is a worldwide pollution. And the last is the water clarity estimation using remote sensing. The water clarity is also called transparency or psychic depth. It refers to the depth of water body that the light can pass through. It is one of the important water quality evaluation indicators. When we measure the water clarity in situ, we use this, the psychic disk. We sink it to the depth, just invisible, and that is the transparency or psychic depth of the water body. And there are some spectral index often used in retrieving water clarity. For clear water, we use green band. For the highly turbid, we use the red band. And in between, we can use some band ratios. And for the FUI, we can also find that there is a good relationship between FUI and the water clarity. And here is a model we built, use FAI to retrieve the water clarity. And here is a validation. We can get a very high accuracy. And we compare with other models. And we find that our model based on the FUI has a high accuracy. And we apply this model to China, to large lakes and reservoirs in China. When we get the spatial and temporal pattern of water clarity of large lakes and reservoirs in China since 2000. Here is the average of water clarity from 2000 and 2018. We can get the high water clarity in the west and the low in the east, especially in the Qinghai Tibet Plateau, the lake area. There are 3.9 meters in average, but in the east plain lake area, it's only 6.6 meters. And we can also get the annual change of the water clarity from 2000 to 2018. And it rises in overall, but it mainly the Qinghai Tibet Plateau lakes, it significantly rise 10 centimeter per year, but for the east, it's only 0.3 meter per year. And we also get the lake and reservoirs clarity in the Belt and Road area. Here is the average clarity in 2018, and here is the change rate from 2016 and to 2018. And this the water clarity, spatial and temporal patterns results across the Belt and Road region are written in the big data, bigger data in support of Sustainable Development Goals 2012, which is published by our institute. And this year, we also calculate the large global lakes water clarity products. And we see the large global lakes have become more transparent in the past 10 years. The water clarity of large lakes showed a fluctuating upward trend from 2010 to 2020, among which water clarity of more than 51% of the more than 1,000 large global lakes increased, especially in Africa. And these results are written in the book, the report in the 2012 this year, which have just been published by our institute. And here are the references of our published papers about what I have mentioned in my presentations. And thank you.
Thank you very much, Professor Li, for this very interesting presentation. Before going and entering into the Q&A session, I am kindly asking all participants to switch on the video because we are going to take a group photo now. So our collaborators will be taking it. So please switch on the video. Have a nice smile. Okay, thank you. Okay, we have a few minutes left, around 7 minutes left, where we can open discussion, and would like to open this Q&A session. Again, very interesting presentation, Professor Li, very timely for me. I'm starting these topics this week with my students.
Thank you.
I have a few questions, but before my question, I will introduce a couple of them introduced by, raised by the audience. So the first question is there any possibility, technology, that remote sensing be applied to conventional parameters estimation like TDS, COD, BOD, chemicals?
A very good question. And many workers or experts in the water environment protection, they often ask me the similar questions. They want you to remote sensing technology to monitor all kinds of water quality monitor parameters like COD, BOD, TP, TN, etc. Well, unfortunately, remote sensing, optical remote sensing, can only monitor some water quality have optical features like chlorophyll. It has very specific absorption reflectance features. It's green, right? And also the suspended matter it will reflect more light, and it will we can tell the yellow reflectance. Well, also there are some organic matter which can also absorb the blue light, and this kind of parameters are we can retrieve very accurately by the optical remote sensing, and we can also monitor other like the algae bloom, the aquatic plants, and the water clarity. This kind of water quality parameters that we can tell from the color, the water color. Well, for the TP or TN, which can control the growth of the algae. If we have more the TP or TN, the chlorophyll can grow well. So we can also actually we can estimate TP or TN or other water quality parameters by the indirect relationship with the water quality that have specific optical features. But this kind of relationships are not very stable. In this lake, maybe the relationship are this kind of relationship. Maybe in other lakes, the relationship can change. So if we have concurrent in situ measured water quality parameter measurements like the TP or TN, in this lake we have concurrent measurements. Maybe we can optimize the model, and then we can estimate it more accurately. If we don't have concurrent in situ measurements of this kind of water quality parameters like the TP, TN, and the accuracy will decrease. That is my answer. It's a little long, sorry.
Oh, thank you, Professor Li. I used to say to my students that remote sensing can retrieve or try to retrieve information about those elements that they change the color of water. So if they don't change the color of water, it's very difficult to do it directly. Maybe we can try doing this indirectly with indirect relationship. Anyway,
yes.
Now I give you a tough chance. So 30 seconds to answer to the second question, how institution can make aware on deterioration of surface water through remote sensing so they can timely make aware us, okay, that water is deteriorating. So very briefly, 30 seconds.
Sorry, I can't, can you repeat the question?
How institution can make use of remote sensing to detect water deterioration and advise the users that the water is deterioration? Yes, water deterioration, water degradation. That's the question.
Water dilation, degradation. Can you explain?
Maybe the question is related to the water quality decrease. Okay?
Okay.
From user point of view. So how user can be make aware that water quality is decreasing, is deteriorating.
Okay.
Very brief.
Okay. We can use different indicators. Like the water clarity is one kind of indicator. It's easy measurement of the water quality in control. Actually, in our SDG report, we just use the water clarity to divide to define the water quality around the world, the global lakes. If it decrease or increase, it's good or it is bad. This is a good indicator. And in the future, we also will use the traffic state. And I think it's also another good indicator, but we have to maybe optimize the model in the future. Yeah, thank you.
Okay, thank you very much. You were very brief and very difficult. We have a few seconds left. I would like to introduce soon. So this session is ended. And I would like again to thank you, Professor Li, for your very nice presentation, and thank everyone for participating to this event. It will be starting soon. Next session, next presentation within the frame of SDG 2.0 hunger. Presentation title: Bigger Data in Support of Sustainable Crop Production System. Before that, if I can have 10 seconds within this topic of water and remote sensing of water, let me announce that there will be in December here, hosted by AIT, first International Symposium of Earth Observation for Integrated Water Resource Management. I will be posting the link here, so see you at that time. Thank you, everyone, again, for being with us for this event. And that's it for now.
Thank you for the opportunity, and I hope to see you again in the future.
Yes, I will be contacting you and hopefully working with you. We have several things in common.
Yeah.
Thank you very much.
And nice to see you, and good afternoon, everyone.
Thank you, Professor Li, and thank you, Dr. Verdis. So please don't go. We will come back soon with the next special lecture. See you soon. everyone, welcome back again. So we are going to have a very intensive schedule today. After the lecture from Professor Li about SDG 6, water quality. So now we are having our second invited lecture by Dr. Lijun from Information Research Institute, Chinese Academy of Sciences. And she's going to present us a lecture about the SDG 2, Zero Hunger. So her topic will be the big Earth data in support of a sustainable crop production system. Dr. Lijun is an associate professor at the Aerospace Information Research Institute and also International Research Center of Big Earth Data for Sustainable Development Goal. She is also the Deputy Director of the National Engineering Research Center for Remote Sensing Application. Her scientific career encompasses remote sensing for land use change and its impact on food security and agricultural sustainability. She is the coordinator author of the chapter of SDG 2, Zero Hunger, in the annual report of Big Earth Data in support of Sustainable Development Goal by the DBA program. And she manages several research programs emphasizing the land use change and its impact on sustainability of agriculture, and also funded by different organizations like the National Natural Science Foundation of China and also Ministry of Science and Technology of China. And also she has, her research has been published in many scientific journals. So today she brings her topic regarding to SDG 2, which is again, very interesting topic for our audience, especially I know many of our government and also the researchers are very interested in the food security and agricultural issues, which are in there, also the main focus in the Southeast Asia. So I'm very happy to invite Dr. Lijun to provide her lecture today. Dr. Zuo, please.
Thank you, Dr. Xue. I will share my PPT slides. Just wait for a moment. Could you see it?
Yes, yes, perfect. Yeah, please
okay.
show the full slides.
Okay.
Thank you.
Thank you. It's my pleasure to have chance to share with my researchers here. And my topic today is about big Earth data in support of sustainable cropping systems. As we all know, the 2030 Agenda for Sustainable Development was adopted by the 193 member states of the UN in 2015. It represents commitments to address the three dimension, social, economic, and environmental issues that our human being faces, and in very comprehensive way in our human history. So for all the 17 SDGs, SDG 2, it aims to end hunger, achieve food security, and improve nutrition and promote sustainable agriculture. It includes 8 targets and 14 indicators. For all the 8 targets, we can divide them into 3 types. First is food demand, and then food production, and also national actions. For all the 14 indicators of SDG 2, 9 indicators belong to Tier 1, which means conceptual of the indicator is clear. Also,
excuse me, Dr. Zuo. Excuse me, we cannot see your slides moving.
Is that okay? Let me
It's
try.
Okay, it's okay. Yes. Could you please show the full screen so we can see it clear?
Okay.
Thank you.
Is it okay? So for tier 1, the indicator, the concept of the indicator is clear, and the methodology have been well developed. And more than 50% of the country and of the population where the region where this indicator is relevant is available. So this belongs to tier 1. And 5 of these indicators belong to tier 2, which
Excuse me, Dr. Zuo, you are muted. Sorry. Please unmute your microphone, please.
Is
yes,
it okay?
Yes,
is that
okay.
Okay?
Yes,
no?
yes.
Okay. And the screen is also.
Could you show the slides? Show the
Yeah.
full screen.
How about now? How about now?
No, we do not see the full screen.
Okay, let me check. Is that because I'm
using two screens?
I'm using the no. Let me check.
Or you can share the screen again and try to share it again.
Okay, yeah, I will do it now. How about now? Could you see it? The PPT slides.
Yes, we can see, but it's still not the full screen.
Okay. How about now? Is that okay?
Yeah, can you try 放映幻灯片? Sorry.
Okay. Yeah, I have tried. In my screen, it is full screen.
Full.
Yeah.
Okay.
Oh.
Okay, never mind. Please go ahead. Yeah. Yes.
Okay. Yeah, thank you. Yeah, for tier 2, they have 5 indicators, and yeah, they have methodologies, but data is not available. For all the 14 indicators, most of the indicators, the custodian agency is FAO. 9 of the 14 is FAO, and every year FAO will publish the progress of each indicators, and most of the indicator they're in charge is estimated by statistical data. And the official from FAO, they said supporting the implementation of new and cost-effective data collection tools is one of the 4 strategies to measure SDG progress. So among all the 14 indicators, SDG 2.4.1 proportion of agricultural area under productive and sustainable agriculture is the most comprehensive one. In this table, we can see this indicator includes 11 sub-indicators. There includes all 3 dimensions. For example, land productivity, profitability, and they belongs to economic. And then it also includes many sub-indicators which belongs to environmental dimension. For example, soil, health, water use, fertilizer pollution risk, pesticide risk, biodiversity, and so on. If we can monitor this indicators, I think we can tell how sustainability the agriculture system is. So most of our research then focus on this indicator. We mostly do the research in the China scale, national scale, to monitor the sustainability of cropping systems. We started from cropland. We monitor cropland change, and then we monitor the cropping intensity, which is represented by multiple cropping index. We also mapping crop distribution, and based on this, we estimate the crop production and its environmental impacts. And then we also estimate the yield potential and the reducible environmental impacts. In this, so we can know how much we can improve in the sustainability of the cropping systems. For the cropland, we actually use variable interpretation to get the land use map. We firstly identify the land use type based on the remote sensing images with high and middle and high spatial resolution. For example, Landsat, Sabres, and 环境1号, which is launched by China. Then
Excuse me, sorry, Dr. Zhu. Oh, we could not see your slides moving.
Oh,
could you
okay.
Please,
I think maybe the problem is I used the internet. Yeah, I don't use the Zoom app, but just on the website.
I see. So please, please move your slides when you are talking, because we only see the same slides. It does not move.
Okay.
Sorry.
Thank you. No, it's my problem. Sorry. Yes. So we developed the land use map for year 2000, and then we check the changes based on the satellite image for every 5 years. That means till 2015, and now we are updating the land use map in 2020. And this is the land use map in China from 1980s to 2015. And from this map, we extract cropland, and we can see the upside one is the distribution of cropland. The orange represent dry land, and the light green represent the paddy land. We also can get the changes of cropland. For the green color, it is where the cropland increased, and for the red one, cropland decreased. And we also check where the cropland loss, which land use types does the cropland converted into. And we can see most of the cropland converted to built-up land, and they are concentrated in southeast of China, because the economic is developed very quick in this region. And for this new cropland, it's mainly gained in northern China, and most of them are from forest, grassland, because we have some ecology project. For example, the Gray for Green project, which to convert cropland which marginal cropland into forest and grassland. When we look into the cropland loss, we get some interesting conclusions. For example, we found the proportion of cultivated land occupied by built-up land in the total loss of cultivated land increased from 30% before 2000 and then to 31% after 2000. The proportion of cropland loss to urban land was the highest one. Here we actually divided the built-up land into 3 types. One is the urban land. Second is rural settlement. And the second one is industrial and transportation land. For these 3 subtypes, we will see the urban land take largest part of the cropland, but the increase of the proportion that industrial and the transportation land take up is increased 7 times from 1987 to 2010. And the proportion of traditional high quality cropland was the highest in the cropland that converted to rural settlement. It's about 92%. We also look into the new cropland that we gained in northern China, and we found from 1987 to 2010, the area of cropland in the arid and semi-arid region of northern China increased by 14%, and it gradually shifted from the semi-arid agro-pastoral ecosystem to the arid oasis desert ecosystem. The grassland was the major land use type that cropland take up, and the proportion of low coverage grassland increased from 34% in 1980s to 52% in 2000 to 2010. Then, after we get know how the cropland change, we also want to know how the cropping intensity is and how does it impact the cropping system. Here we use the time series remote sensing data to get the multiple cropping index. We firstly reconstructed the time series of the EVI data to remove the noise which caused by cloud mostly. Here we can see some curve of the time series EVI data. Here, if the curve have one peak, we say it is just planted one crop for 1 year. If the peak is 2, then we think let's have 2 crops in different planted in different seasons. And here is the triple cropping index in this figure. Here is what we get. This is the multiple cropping index in China, and we can see for northern China, most of the cropland can just crop 1 times, and for northern China plain, they have double cropping index, and for southern China, we usually planted 3 times 1 year. Based on this, we also used the frontier production function to estimate the multiple cropping index gap. That means how much more we can plant it for 1 year in certain cropland. And this is the result. Then we also check what the factors impede the increase of multiple cropping index. Here we divided the China into several regions, and we also estimate several impact factors. How does it performs in each region? We gather some factors, for example, labors per unit area, income per labor, perfect per unit area, and machinery per unit area, irrigation rate, and rank of soil erosion, and the DEM. Here we find the MCI, that is multiple crop index gap, in southern West China and central China were highest among all regions, with a value of 0.5 and 0.36. And the factors impede the increase of MCI in southwest China are more about physical ones, for example, the topography and soil erosion. However, that for the central China are more about management, such as number of labor, power of agriculture, machinery. So it means for the physical ones, it's very difficult for us to change it. But for management, we can kind of change it. So we conclude the MCI gap closing in the southwest China is more difficult than central China. So we will see that most of the efforts should made focus on central China. Based on this, we also check how much how does the MCI is for this new claimed cropland and this lost cropland, and we can see the new cropland actually have lower potential multiple crop index, while the lost cropland it usually have a high MCI potential. And we also calculate the total total potential harvest area that lost because of the cropland loss, and the potential harvest area that we can gain from this new cropland. Here we find that although the new cropland area of new cropland is larger than those lost cropland, but the potential harvest area gained is less than those we lost. So it's kind of risk. After monitoring the cropping index, we also want to map the crop distribution. How we want to know how the crop distribute in China, and then we can get more knowledge on how the production and the environment impact distribute. Here we use the multiple source of data, including remote sensing data and statistic data. For remote sensing data, we also use the method that we use to get the MCI. We detect the pink of each pixels of the cropland. For example, how many pinks it have, and when the pinks happened in which season. And then we also divided the China into several regions based on the cropping patterns. For example, in northern China plain, the winter wheat usually planted in winter, and the maize and the soybean usually planted in spring. And so based on this knowledge, we divided the China into several regions, and we get the knowledge about which kind of crop it planted in winter and which planted in spring, and some planted in summer. And then we connect these two informations together to allocate the statistic data on to the cropland map get from the remote sensing data. And here is the result. We mapped 14 major crops in China, including maize, rice, wheat, soybean, rapeseed, potato, cotton, groundnut, sugarcane, wheat, sunflower, and so on. Based on this map, we can check how the crop changes in different time. We mainly, because the remote sensing data we used is modest data, it started from 2000. So the crop map here is, we also checked 2000 and 2015. So between this period, the area of maize increased largest by 46% from 2000 to 2015. And the area of wheat and soybeans both fall sharply by 10% and 27%. Among other crops, the area of potato, sugarcane, peanut, rapeseed increased slightly, and others showed a decreased trend. We also analyzed the centroids of most of the crops, and most of the crops, they moved towards west, and it's mainly because of the shift of cropland, and also the change of the multiple cropping index in China. These two reasons has, for most parts, they induced the changes of the crop distributions. We also analyzed the crop diversities because the crop diversities, it have many implications on the production and resilience of the cropping system. Here we find the crop diversity is high in the area of Hu Lai. That means it is less Lai. We can, yeah. So the value for Northeast agriculture zone is lowest, is about 0.9, while that of the Southwest agriculture zone got the highest one, is about 1.41. And the crop diversity decreased between 2000 and 2015. The cropland with decreased crop diversity account for about 72% of total cropland, and it concentrates at Northeast and North China plain. It means most of the cropland in this region, they tend to plant just one crops. For example, in Northeast China, the maize is expand largely in several years before. After mapping the crop distribution, we also want to know how the crop production, how the crop production is and how it change, and what's the environmental impacts that it induced. Here we focused on several indicators. As we said just now, we use remote sensing to has monitored the cropland change. And then we also used the statistic data and the crop distribution map to allocate the production data and get the crop production map. And we also focus on the irrigation water and fertilizer application. For irrigation water, we use FAO coefficients to estimate different crops, how much water they used. And we divided into green water and blue water. For blue water, we just use it to represent the irrigation water. And for fertilizer application, we also use the statistic data. We divided the statistic data into different crops, and also in the whole country to map the distribution of the fertilizer application for different crops. For this, we use spatial allocation method. And then we further use the mass balance model to estimate excess nitrogen and phosphorus application. That means how much we used in this patch of cropland, and how much that the crop take up when it grows, and and then use the difference of these two is the excess nitrogen, net excess fertilizer. We also check the greenhouse gas emissions by several models. First is mass model. This is developed by Physical Institute in Chinese Academy of Science. It is measure the paddy rice. How does the mass emission from the paddy rice field? And we also use the nonlinear models to check the N2O emission from fertilizer application. And also we use IPCC guidelines to measure the carbon emissions because of the land use change from the land use change related with cropland. They will have the carbon emissions or carbon sequences because of the biomass and the soil carbon change. And here is our result. For the production of 14 crops in China, it increased by 66, largely because of increase in maize. It contributes 56% of the total increase, and then it's wheat and then rice. This increase was driven by changes in farm management. As we all know, the irrigation rate increased in many cropland, and the fertilizer was applied in most of the cropland in China. So this contributes to most of the increase of the cropland of the production change. Land use change, it mostly is the loss of the cropland due to urbanization. It reduced overall production, but the percentage is very small. It's about 1%. For the cropland area, we just have analyzed before. It increased by 2% from 1987 to 2000, and decreased about 0.7% from after 2000, and with a net increase, a very small net increase. And the national average land area intensity, it means how much cropland area were used for per kilocalorie production we produced. This intensity decreased by almost 40%, and it just increased in just 10% of the cropland. It means the cropland was used more efficiently as time passed by. We also analyzed the farm management change and land use change. How does these two factors impact the land use intensity? And then we find farm management explained most of the decrease in land area intensity. And the land use change also offset a little, excuse me, also offset a little impact, which is by farm management. For irrigation water, it also increased total water consumption for irrigation increased by 17%. And most of this increase was driven by maize and cotton, which accounted for 34% and 15% of the change. National average irrigation water intensity decreased by 30%. It means the irrigation water used more efficiently, and the irrigation water intensity just increased in 8% of the cropland. And from the figure, we can also see the farm management was the major factors that contributes to the decrease of the irrigation water intensity. For excess nitrogen, it's the total amount is also increased, but the intensity rose first and then fell down, and leading to a net decrease of 13%. Nitrogen use intensity decreased in 55% of the cropland. And here we can see the farm management explained 89% of the reduction. And land use change also reduced excess nitrogen use intensity. The excess phosphorus also show an increase in total amount, about 161%. The phosphorus intensity, it didn't decrease, but increased by 57%. It's the change rate, the increase rate is slowed down. And the farm management is also the main reason for the increase of excess phosphorus use intensity. Land use change it offsets the increase by 1%. For greenhouse gas emissions, rice methane was the leading source of the greenhouse gas emission. It accounting for 83% of total agricultural emissions. But it also decreased very largely by 50%. National average greenhouse gas emission intensity decreased by 50%. The decline occurred across 62% of the cropland. If we combine all the 5 indicators together, we will see the intensity of all 5 indicators declined across 18% of the cropland and increased on just 2% of the cropland. So it means in China, most of the cropland it tends to be used more environmentally efficiently. But we also analyze the impact of land use in different regions. When we dive into different regions, we see the land use actually have a larger impact on regionally. For example, in Southeast China, land use change have decreased the production all the time, and the percentage that decreased climb up as time passed by. Before 2000, the decrease is about 18%, but after 2000 is about 70%. And for the Northwest China, the land use change has increased the irrigation water use. And before 2000, it increased about 19%, but after 2000, it increased irrigation water by about 84%. So it tells us, although the land use change didn't impact the overall environmental impact in China, but it have great impact in regionally. After the estimation of the production and the environmental impacts, we also estimate the yield potential and the reducible environmental impacts. By doing this, we want to know how much we can improve for the sustainability of cropping system. We use remote sensing crop yield models to estimate how much we can increase the crop production. And we use the input-output models to check if we fix the production, how much fertilizer we can reduce. And we get some conclusions. That is, if we closing yield gap in the major agriculture zone in China, we will have about 5% and 8% more production for rice and wheat, respectively. This increase can meet the projected food demand in 2030. And if we do not consider about the increase of the production, we just fix the crop production and how much the fertilizer application we can reduce. The result we show is about 17% and to 19% of the fertilizer application. It can be reduced. without decreasing crop production. So there's still room for us to improve the sustainability of the cropping system. This is all what we have done now. In the future, we also have some plan. For example, we would like to monitor more indicators reflect the sustainability of cropland use based on big Earth data. For example, soil erosion we didn't look into in the former studies, but in the future we will focus on this to expand the indicators that we're looking. And then we also want to do some food security analysis based on combination with some social and economic factors. For example, we would like to employ the food demand. That means how much food we actually need in this research. Then we will also see if the crop production is what a crop product produced is what we need, or we just produced more maize and less soybean, which is cannot match with what we need. Okay, and this is all what we have done now, and thank you.
Thank you very much, Dr. Zuo, for very informative presentations. So it's very happy to see that you produce a lot of data products to support the sustainable crop system in China. So we have some questions from the audience. Maybe I will try to bring them out and we can have an open discussion. So there is one, it's like a comment, but I would like to, it looks quite interesting. I would like to bring for discussion. So one of our audience mentioned that the hazard and urbanization is also responsible for the loss of soil and also to impact the food security in many developing countries. And also the sustainable policy will be the factor which can drive the food security issues. I think this is quite a link with what you are planning to do in the future, so to incorporate more factors in your analysis. So could you please share your opinion on these comments? I think our audience are interested in whether like hazard, like urbanization, like the policy can be incorporated in such kind of analysis, and then can help with better, analysis about the cropping in the future.
Yeah, urbanization is a very serious problem for food security, I think, in developing countries, because the population is increased and the economic is developed. So urban is actually expand. And for rural area, it also expand. And usually the cropland near the rural settlement, they have the high productivity. So it's also a problem that we need to focus or look into in the future, besides the urbanization. And for urbanization, we can also see, because the urbanization and the development of the economic, the consumption of the food will increase, but the urbanization it take up cropland. So this is this problem. They have double pressure on the food system. So this is about the urbanization. For the policy, yes, it's also actually for food system is it impacts a lot by the policy. For example, in China, we have the some project or engine project, just like convert the marginal cropland back into grassland and forest. So it will decrease the cropland, but it can sustain the environmental system, which maybe it can improve the food productivity or food or yield. So this questions is very is worth to investigate. Yes, I think.
Thank you, thank you. We have another question from the audience. Is matching the right land suitability with suitable agricultural products based on land type important for achievement of SDG 2? Could you please also share your, yes, the question is whether matching the right land suitability with suitable agricultural products based on the land type is very important for achievement of SDG 2.
Yeah, I think it's very important because actually now we also do a research to see how could we optimize the crop planting structure, the structure of the crop distribution. How could we optimize it to increase the production and then decrease the environmental impact? And we see about 20 to 50% of the decrease of the environmental impact if we can optimize the crop distribution. So this is an ongoing research that I didn't share here, but it indeed have a lot of have a lot of room to improve by match the suitable land use to suitable agricultural product. Yeah.
Okay, thank you. So maybe the last question is from me. I'm just personally interested. In your last slides, you have mentioned that to close the yield gap, it's possible to bring higher productivity and also reduce the waste of fertilizers, the discharge of fertilizers. Can you please explain a little bit more detail? What are the practice or activities to close the yield gaps in China?
We actually have applied some precise fertilizer application. That means we measure how much the crop is need in different phases of its growth. As it grows, how much fertilizer is need and how much water it needs. Then we irrigate and apply the fertilizer accordingly. So by use this this method, we can increase the production and then decrease the fertilizer use.
Okay, thank you. I think we are almost at time, but before we closing today's section and last lecture, I really hope that that we can have more chance to maybe communicate perhaps with the expert in Thailand and also expert in the Southeast Asia on agriculture. I myself is not working on agriculture, but perhaps many experts who are more clear about agriculture and about remote sensing application in food security management. So I hope there will be more communication with you, and also your technologies and your research could be expanded to this region and to help with larger sustainability. Okay, thank you so much. So thank you very much all. oh, sorry, I guess I forgot to call for a group photo for this section. So may I just take the last minutes? I request all the audience, please turn on your camera again, and then we can. Thank you so much for joining us today. And we are going to have the next 2 lectures on Thursday. So we are looking forward to seeing you again on Thursday. Thank you. Thank you very much. Bye-bye. Have a nice day.
Bye-bye.